This is Chapter 5 on sampling distributions, and I'm not going to go over sections 1 and 2 in any detail, but I'd like to do just a very quick review of them. So what we saw earlier was that if we assume that the underlying population was normal, how we could draw inferences about two things that are of quite interest. One would be mu, the population mean, and the second would be the difference between two population means. And if we were interested in these two things, there's a couple of inferential statistics that we could have. We could think about using null hypothesis statistical testing or create a 95% confidence interval. And so we could do both of these things for both a population mean and the difference between two population means on the assumption that our underlying population or population was normally distributed. So now we're going to continue on and think about the chi-square distribution. And the chi-square distribution also is going to assume that the underlying population is normal. But previously, our targets have been either the population mean or the difference between two population means. And now our target is going to be variance. Now, I admit in my language I'm sometimes going to be a bit sloppy, and instead of saying variance, I might say standard deviation. But obviously, if you can estimate the variance, it's trivial to calculate what the standard deviation would be. So the distribution we're going to use is the chi-square distribution. And the chi-square distribution has a lot of applications in statistics, but what we're going to do in this section is focus on how the chi-square distribution can be used to draw inferences about the population variance. So how is this going to work? Well, again, we're going to assume that our underlying population is normally distributed. It's going to have some mean, mu, and I'm going to represent the standard deviation here as sigma. Now, as it turns out, mu is irrelevant. Our goal is to estimate this thing, either sigma or sigma squared. So you can just ignore mu in any of these calculations. This is what we're going to focus on. So if we think about our underlying population being normally distributed, there's an underlying population normally distributed with some mu that doesn't really matter and some value sigma that we're trying to estimate. Let's assume we went into this population and we took a sample. And on the basis of that sample, we calculated a value of chi-square. And the way we would calculate that is to take, I think I'm going to go lowercase here. I'm going to calculate the standard deviation, or might be better to say the estimate of the population variance that I'm going to represent as S squared. We're going to multiply that by n minus 1, and then we can think about what would happen if we divided that by the true population variance. And we could take this value and we can stick it on a number line. And just as a reminder, where does this come from? It's the sum of all the yi minus y bar all squared divided by n minus 1. And then we could repeat that process. We could draw another individual from this population. We could calculate S. We know what n minus 1 is, and the n minus 1 is going to be constant through each of our samples. The variance, there's another point. Take another sample, same n minus 1, calculate a new value of S squared, use the same old sigma squared, and what we get over time, is the set of all possible values of chi-square. So this is going to be a probability density function. So we've got a probability density function that looks like this. The probability density function, and on the x-axis we get different values of chi-square. On the y-axis, the probability density of chi-squared, and we can think of each chi-squared as being S squared n minus 1 over sigma squared. And then if we consider the set of all possible, we'd have our random variable. I'm going to represent the random variable as this is meant to be a capital chi squared is equal to, and now it's going to be a capital S squared onto n minus 1 divided by sigma squared. And again, throughout this course, we've made a big deal about the difference between, let's say, little y and big Y, little t, big T, little y bar, big Y bar. Whereas these would be the individual values we get when we actually did the experiment once. This would represent the random variables, the set of all possible values of these guys. And the same thing is going to happen here. When we do our particular experiment, we get a single value of s squared. If you consider all possible values of s squared, they could be represented by this random variable, big S squared. Similarly, lowercase chi squared would be the value we get when we actually did the experiment that one time and calculated our chi square. This capital letter chi squared is a random variable, the set of all possible values of this. So we've got this random variable. We're going to represent it as capital chi squared. It's equal to capital S squared onto n minus 1 divided by sigma squared. So it's a random variable. And because it's a random variable, it has a probability density function. And we can refer to the probability density function as a sampling distribution. And because it's a probability density function, it's got to have a formula. And there's the formula. To understand this formula, perhaps we can compare it to the formula for a normal distribution and the formula for a t-distribution. So remember, in the case of the normal distribution, it had two parameters, mu and sigma. There's sigma and there's mu. And then we've got this value of y that we measure. And then our probability density function, it's a function. So it just acts like a meat grinder, and we take y, and we shove it in the meat grinder, and what comes out the other end is the probability density function. So what this represents is the probability density associated with whatever value of y it was we shoved into our meat grinder. And in the case of the t-distribution, we've got a single parameter, mu, and there it is right there, and there it is right there again, there it is there, and what we do is we get our particular value of t, or in this case, t squared, that's shown right here. We put t in here. What comes out the other end is f at t, which is the probability density associated with a particular value of t that we recorded. Now, as it turns out, in some ways there are some similarities between a chi-square distribution, shown down here, the probability density function of that, and the probability density function associated with the t-distribution. One thing they got in common is they have a single parameter, and that single parameter is nu, which is equal to the number of degrees of freedom, which is equal to n minus 1. So there's our values of nu, and what we do is we calculate our single value of chi-squared, small s squared, because it's based on our single sample, onto n minus 1, sigma squared. That's the value of chi-squared that goes in there, and what comes out is the probability density associated with that particular value of chi-squared. Now, as we saw in the case both of the normal distribution and in the case of the t-distribution, we typically don't use these functions. I mean, these functions are just presented here, the whole idea being what we're dealing with is random variables, and these random variables have probability density functions, and this is the idea of what a probability density function is. In practice, in this course, what we use are tables. So here's our t-table that we saw before. Remember how our t-table was set up. It had the number of degrees of freedom, because remember we've got to have that parameter nu, which is equal to n minus 1, which is equal to the number of degrees of freedom. And then across the top, we've got these numbers here that show this portion of the curve. And something very similar is going to come down here with our chi-square table, although you're not actually going to have to do any calculations of chi-squares on the written exam. I'm just going over this so that you understand the basis of a chi-square distribution. But you can see again, very similarly, here you've got the number of degrees of freedom, nu. Here you get a bunch of probabilities that show the probability of the value lying in this area. So if we think about the t-distribution and the chi-square distribution, they do have some things in common, but they've also got some differences. So one of the differences is that in the case of a t-distribution, we saw it was always centered on 0. In the case of a chi-square distribution, it's not going to be centered on 0, but what we discover is, or what statisticians have shown, is that the mean of a chi-square distribution is equal to nu, the number of degrees of freedom. The second difference between a t-distribution and a chi-square distribution is that the t-distribution is symmetrical, whereas the chi-square distribution is asymmetrical. And so we'll stop there.